Good morning, pre-calculus. We're going to look at section 5.4, still focusing on rational functions. Today we're going to take a closer look at rational equations and inequalities, solving rational equations and solving rational inequalities. All right, here we go. So first let's take a look at rational equations. Rational equations are in the form of some polynomial of x over some other polynomial of x equals 0. And again, right now we're dealing with these as polynomials, but later we see that they don't always have to be polynomials. We can see some weird stuff there later on. But right now we're looking at these. And this is in standard form. They don't always end up in standard form. If it's like this, then we really just focus on whatever makes the top equal 0. Because when the top is equal to 0, it doesn't matter what the bottom is. The whole function is going to be 0. And when I say it doesn't matter what the bottom is, of course there is an exception. If the top equals 0 and the bottom equals 0, then it's undefined. That is not a solution. We call that an extraneous solution, and we'll see some of those coming up here in a moment. So it's all about solving these. As then I said, it's not always going to be in that form to start. Let's take a look at an example. Suppose I have x plus 3 over x equals 4. Now here's an example where it is not in standard form. I could multiply this by x over x and get x squared plus 3 over x, subtract the 4, multiply that by x over x, and have x squared minus 4x plus 3 all over x equals 0. Or I can just focus on this equation. Now the thing that gives me a hard time is the x down here. I don't want that x there. So I'm going to make it go away using an old trick where we're going to multiply everything by the common denominator of x, clearing the fractions. So as I multiply it across, all of the denominators go away, and I end up with x squared plus 3, the x's cancel, equals 4x. Subtract x squared minus 4x plus 3 equals 0. And if you follow what I talked about in the beginning of setting this into this form, this all over x equals 0, it's the same thing. This is the numerator. This is what we want to focus in on. Now this one's not so bad. This one is easily factorable. I can think of minus 3 and x minus 1, setting each factor equal to 0. I'm at the bottom of the screen here. Setting each one equal to 0, I get x can equal 3 as one solution, and x equals 1 is the other solution. So there are my two solutions. The other thing that's going to become an issue is, in the original function, if I look at this original, or the original equation rather, as I look at the original equation, I have a restriction here. X cannot equal 0. This equation is not defined when x equals 0. So as we solve it, we want to keep that in mind, and then at the very end, looking at our solutions, and are any of them restricted values? If so, then that solution is an extraneous solution. All right, let's take a look at another one. Suppose I have x squared plus 4 over x equals 20. Again, not in standard form. I can use the trick to get rid of all the fractions, all of the denominators, by multiplying everything by an x. And I get x cubed plus 4 equals 20x. Subtract x cubed minus 20x plus 4 equals 0. Now notice here, it's not a quadratic. We don't have any nice, quick, easy ways. Quadratic formula isn't going to work here. Factoring isn't going to work here. How can we solve this? How are we going to be able to deal with this? And this is one we can do on our calculator. So let's talk about how to solve these on the calculator. Notice in my first example, I didn't need a calculator, so that kind of question could be on the non-calculator part. But this one, as we'll see, the answers don't come out very nice. We would certainly need a calculator. So the strategy is all about graphing and using the calculator. I could graph this equation and see where does it equal 0, what are its zeros, or what are its roots, or what are its x-intercepts. Or, right from the very beginning, I could graph this in y1 and that in y2 and see where they intersect. The answers will be the same. whether I graph this equal to 20 or whether I graph this and see it where it is equal to 0. I'm going to start with the original equation here. So in my y1, I'm going to plug in x squared plus 4 divided by x. I'm going to put that in my y1, and then in y2 I'm going to put in 20. Now the x values, I have no idea what they're going to be. I do know I have a restriction, by the way. Did you catch that? I've got a restriction here because of the denominator. X cannot equal 0. So if one of my solutions come up as 0, I'm not allowed to have it. 0 is not going to be a solution. If I plug in 0, I get 4. So 0 is not going to be a solution. But now as I graph this, I have to think about, well, what's a reasonable domain? What's a reasonable range? So as I go to my window, the x's, I'm just going to go from negative 10 to positive 10. That seems to be pretty safe. Scaled in ones. The y's. Now I know that I'm going to have 20, and everything happening around 20 is what I'm really interested in. So I'm going to go from y equals 0 to 30, scaled in 5s. And I don't know what this part's going to look like, but I'm going to get that line at 20, and I want to see where this crosses that line at 20. So if I hit graph, so there's the crazy rational function, and there's the line y equals 20. Remember, my x's went from negative 10 to 10. My y's from 0 to 30. So now I need to calculate the intersection points there on my graph. So I'm going to use the calculator to do all the work for me. Second calc, intersection point. On the Casio users, gsolve intersection, it'll snap to the first one. Hit the over arrow, it'll go to the next one. Hit the over arrow, it'll go to the next one. The TIs, we have to be a little bit more careful here. I have to bring my little, drop a pin on this side, hit enter, and there. So then it'll look forward for the first point of intersection, and there's the first point. X equals approximately negative 4.5689-ish. Find the second one, intersect. Now I need to pick some points on the other side of this function. I'm looking at the little x readouts here. There we go. Well, not that high. Up there, that looks good. And then on that curve. So now I picked on this side of the intersection point, and it's going to look forward. Found that one. X equals 0.2004 approximately. And then finding the other point, second intersection. I need to drop my pins close to that point over there. So you can see my little pin getting closer and closer to that point, right about there. And now it's going to, starting on those 2 points, it's going to look forward to find the point of intersection. And there it is, 4.3685 approximately. And just as we kind of predicted, not very nice numbers here. Difficult numbers to work with. All right, let's look at an application of this now. Let's look at an application of solving a rational function or rational equation. And in this problem, suppose I want to design a soda can. And we're going to say that the soda can is cylindrical, nice, well-behaved cylinder. We know all the formulas for a nice cylinder. The important dimensions of a cylinder, it has two, is the radius and the height. And what do I need to know about this cylinder? Suppose I want this to be, suppose I want to make sure that I've got, it's a soda can, so I want to have a volume of 355 milliliters, which we also know is 355 cubic centimeters. And I know that I want the height of the can, and as I'm looking at this, I'm going to talk about the surface and the volume, the surface area and the volume, because I want to use the smallest surface area possible, and given a radius and a height, or maybe I want to do the smallest volume possible, or given a volume, or given a surface area. Let's look at the case where I'm given a surface area of, so my volume is 355. So I know that for a cylinder, the formula for volume is the area of the base, which is a circle, pi r squared, times the height. And the surface area is the two bases, which are circles, 2 pi r squared, plus the lateral, which is the area of the base. If I unfold it, it's a big rectangle. Area of the base times the height, which is 2 pi r times the height of h. Now we want to have let's say we want to have a fixed surface area. I want the surface area to equal, or no, I've got a fixed volume. I want my volume to equal 355 cubic centimeters. And I want to find the smallest possible surface area that will give me that volume. I know I want my soda to have exactly 355 cubic centimeters inside it. What should my radius and my height be so that my surface area is the smallest possible amount? I'm using the smallest amount of aluminium here to make the tin. All right, so my volume is 355. So 355 equals pi r squared h. If I solve that for h, I get 355 over pi r squared. Now, I can rewrite the surface area as a function of the radius. So my surface area as a function of the radius is going to be 2 pi r squared plus 2 pi r h. But what's the h? 355 over pi r squared. And we can see that the radius is the variable. And here it is. I'm going to have a rational function here. This radius will cancel with one of those, but I'm still going to have an r over there. If I clean this up a little bit, the function I'm going to be working with is going to look like this. The surface area as a function of the radius is 2 pi r squared plus, let's see, the pi's will cancel here. 2 times 355 is going to be 710 over my radius. So there's my equation that I need to work with. I'm going to do the calculator. We've seen this before. We kind of know what this is going to look like. So I go to my y equals. I'm going to clear this out. Clear. I'm going to put this formula in. I could put this formula in right from the substitution without doing any simplifying at all. 2 pi, my variable button, squared, 2 pi r squared, plus 710 divided by my variable button, the radius. Now, as I go to make the window of this, I have to think about what type of window. And do we remember what graph we're expecting here? What type of graph we would expect from this? If I have my surface area as a function of the radius, 2 pi r squared plus 710 over r, we should remember that the function is going to look something like this. This is what I'm looking for. And of course, the minimum value is going to be right here. And this would represent my radius, and this represents my surface area. Radius in centimeters, surface area in square centimeters, the minimum value. So this is the graph I'm expecting. Knowing this will help us decide what the windows should be. Negative values of x don't make any sense, so I'm going to go from 0 to something. Now the radius, how big does the radius need to be? 10 centimeters, I think it'll be a lot less than that. I'm just going to go to 5 centimeters, scaled in 1 centimeter increments. The y values of the surface area, 0 to, I have no idea what the surface area could be. Let's go to maybe 1,000. That might be way too big. Scaled in 100 increments. But again, you just want to kind of get an idea, graph something, and then make changes when you see what it looks like. So I'm going to hit graph here. Oh, I think I'm pretty good on the y's, but the x might be too small. The x might be a little bit bigger, the minimum value there. Let me add a bunch of x's here. So I'm going to go back to my window and make it go to 10 centimeters and graph it again. There we go. That's what I'm expecting. See, this is what I'm expecting. There's my minimum value. So Casio users, gsolve minimum. TI users, second trace, calculate button, calculate the minimum value. For the TIs, I have to drop a pin on either side of the minimum. Over here and over there, find a minimum between these two over that domain. And it looks like I'm getting the point here is 3.837-ish. And the surface area here is 277.545. So this means if I make my radius of my can 3.837 centimeters, I will have a minimum surface area of 277.545 centimeters. The other thing I might want to know is what is the height? What is the height of this can here? And we can use the formula from before. The height is 3.55 over pi r squared, and I know the radius now. So I could substitute this in, 355 divided by pi times this square, and I could find the corresponding height as well. So here we go with an example of solving a rational equation and an application to it. So now I can know the dimensions of my can and the smallest possible surface area I can get to reduce the amount of material it takes to make the can. All right, we'll take a break, look at the first few examples in the homework, look at the equations, and when we come back, I'll start looking at the inequalities.